So I managed, like I figured out how the projector thing works. So I did want to kind of show you a little bit of the Canvas side first before getting into like some of like of the material for today. So let me see if I can show you that. Uh, where is like no this like screen option? What is happening here? Like if I am I going to get stuck by not being able? Ah, finally. This is crazy. Okay. And then oh my God. Okay. Okay. So finally, let's see. So basically, what I was telling you in terms of like the Canvas side is that there is a lot of papers that I put in there. No expectation whatsoever that you would go through them. Like, there are tons. It's more like, eventually, like I think for the first 1 or 2 months, we just go a bunch of basics, have everything in place. But my goal is that if you were to like randomly click on one of these papers, that you can kind of like more or less start reading it and it doesn't feel like alien language. It's kind of like more like let's just be on the same page on how things are called, like how the diagrams are supposed to be read. But then you're gonna kind of like again, I'll like once we get there, I'll decide like what would make most sense. But like it's more like I just want to get to a point where like anyone can read like open like a random paper and at least like the notation is clear, like the terminology is clear, like all of that stuff. Um, because like like that's especially mathematics or physics like that is like 50% of the way or even more like just like understanding what people are saying like so that's useful to know. So if you scroll down like you'll see like at the top I will always keep the things that we're actually doing during class. So for example I will be updating this you know list of like tensor problems. I'll probably just write them on the iPad because like I'm not super fast at the moment, like doing this on the computer so that it looks nice. But then whenever I write like the problem for you to work on, um, I'll write it here and like if I intend for one to be like an actual assignment problem, then I'll clarify it. For today, I did want to discuss at least one or two of these during class so that make sure like this is making sense. Uh, and then um, and then yes, I was saying um like Boltzmann machines is like a topic which has to do with tensor networks. Okay, this is kind of like what I'm calling advanced mathy stuff, which obviously is not that it's like a perfect classification, right? It's how I sorted it. But for this, I mean like, okay, you really have probably needed to have taken a bunch of courses. Like if you want to like go into more detail of one of these papers eventually. So and then there's like all these like lecture notes that I found. And again, I will recommend, I'll be like, well, if someone wants to read some more about this, you can look at this specific PDF. But I kind of like did break it into topics so that you could see how things are sorted out. Uh, and then like these like at the bottom, they're actually more useful. Uh, so for example, like, oh, this one is cute. Like I like, and again, like once we have talked for more time, you can probably take a look at this. But like these are some examples of tensor networks, which look really cool. But this one is like a nice paper because it just goes like into the basics of okay, some of the stuff that we were talking about earlier, right? Like a number is just like a circle or like a disk. A vector has like one edge coming out. A matrix has two edges. A three tensor like has three edges and so on. Um, so it kind of goes over the quality is not the best like on the computer, but like if you open it, like it would be fine. And it kind of like gives you like some pseudocode or whatever if you want to plot it like on Py. I think this one uses PyTorch. So you kind of like see like that like like the tensor networks which are really nice like to appreciate how they look in practice. Obviously we'll get to more complicated examples later on, but this is like a good review, and again I'll mention it like later if you want to take a look at it. Um, and then towards the end, these are more like if you're more like in the programming side of things, like these are some like references that you can use if you want to download and even play with it in the meantime. Although I'll probably try to have like maybe like a class or two where we kind of like
like go into more like details of how these things work. But there's like the iTensor library, um, which you can use like to represent like to do computations with tensor networks. And then, oh my God, let me see if I can move this. And then there's this other one. I mean, iTensor like there's like a version that works on Julia, so like you can download Julia as well if you haven't used that before. Oh, oh my God, like I subscribe to GitHub Copilot because I'm lazy. So like it gives you writes the code for you. It's really fun. So like if you like, I mean, I'm sure like this is offensive for those who know how to code, but I'm very like, pragmatic when like, and so I'm like, okay, like I literally was like just to show you how embarrassing it's like, how do I find the terminal on the on the desktop? I was like, it's very convenient. So like yeah, but I'm just saying like we'll try to kind of like get to that something more like, oh, how would you actually write this like on a computer, like on or like one of these programs, so like you see it. But I'm just saying, in the meantime, if someone is really curious about that, like there are all these tutorials and worked examples, so you can take a look at them if you want it for now. Uh, but again, like the way I organize it is more like I wanted you to have like a repository where if after the course, if you ever need to find something, you can kind of like start here and then like branch out. So it's kind of like even for myself, it's kind of like for my future self. Oh, I want like a place where like kind of like the things are sorted for me, because I do think this is a fun topic to learn about. So like that was to the benefit of everyone. Um, okay, now let me see. Is that okay? Is that making sense? And as I was saying, like probably after today, I may give you like one or two problems for you to think about over the weekend. The but like yeah, like I did want to discuss some of what I wrote on that PDF assignment to see if like everyone found like the correct answer if you tried it. Okay, so let me stop sharing. Okay, now let me see how this looks like. If not, again. Okay, and then let me connect the output to the table. Oh, here they are. Mhm. Why is this working? Why is this? Okay, sure. Wait. Mm. Okay, fine. Oh my God. This is the most confusing computer podium I ever used ever. And if the phone is that way, like then I'll switch to the board, but that way I can just share the another sound in this very fast like this. Um, okay, so before like working like those examples, let me just introduce like a super quick notation, which is like this Kronecker delta, which is like a convenient one, which I don't know if everyone has seen in the past. So let's call it delta ij. So this is usually called like the Kronecker symbol. Okay, and the idea is that this is something that takes values either 0 or 1.
Okay. So it is a one if I equals j. And it is zero otherwise. Okay, so this is zero otherwise. Now, let's do what a round down of this. So for example, that would say that delta 1, 1 is 1. Like for example, delta 2, 2 would be also 1, but say delta 1, 2 would be 0 and delta 2, 1 would be 0, right? So like the moment like two of the indices are different, like just like without 0. That is convenient because if you think about it, those are actually the entries of the identity matrix, like of a particular size. So, if you think of the identity matrix of a given size, well, I mean, what is like the identity matrix? It's just 1, 0, 0, 1, right? And this, like, based on what I was just saying, is delta 1, 1, delta 2, 2, delta 1, 2, and right, delta 2, 1. So in fact, like the entries, like the ij entry of the identity matrix is just like the parameter symbol. I know that I don't know when the quality is on the grade on the screen, but I think it's readable, right? But I also have to be writing super nice of like because there's something you like the some page and that's yeah. And it that's just like nothing it's like a convenient that they got to use. Like for example, if you have like some vectors which are orthonormal, right? Here's like one way to like it is useful even in cases where like having nothing to do with like like the identity matrix, right? Like you could say like that. Here's another example of this notation. You could say like that the vectors v1, v2 up to vn are called orthonormal, right? Well, if you remember what is the point of being orthonormal is that they are orthogonal, right? Like every vector should be orthogonal with every other vector, and that the normal part is that like each vector should have like one, right? So all of those two conditions are very easily summarized just by saying that ei dot vj should be delta ij, right? Because that automatically, that automatically is 0 if I is different than j. And that is just like the length squared, right, of the vector, the magnitude squared, if I equals j. Um, like sometimes when you want to write a formula, it does simplify your life to to have like the character delta around. That's why let me mention it now because I will use like the identity matrix in a couple of times today. It's kind of like this to have this ready to go. Okay, so let me give you an example, like just to go back to like the tensor diagrams. Let me give you an example of where this like it is useful like in terms of like the diagrams. Okay. Okay, let's say that A is an n by n matrix. So again, the way I told you, you can think about it of the matrix in terms of like the diagram. You make a circle or like a box. Doesn't matter too much for us.
Um, I'll put its name here. And because the matrix has two indices, right, I and j, right, like the entries are a, I, j.
No. You can kind of think of one of the legs or like one of the edges, open edges, like representing the index I and the other one representing the index j. Okay.
And then you could have like the identity matrix of the same size. So let's put that one here.
You could have like identity matrix of the same size. I'll just call it I in sub n,
Just to say that there's an n by n matrix, identity matrix.
Well, exactly why I wanted the icon because now I can just copy paste it very easily. So let's copy paste that. And the idea is that each of them has like two edges, right? So you could maybe decide to join these two together and these two together. Okay.
So let's like, I'll kind of try to draw the steps, like divide them by some sort of line.
So like step one, you have kind of like the two separate matrices or like the two tensors on their own. And step two, you kind of like choose to join their
Like open edges. So I'll put them here. And then, well, actually, let me call this matrix C just like for a sec. Like just you'll see why, so that it doesn't get messed up with the next example. Sorry about that. I mean, it's the same idea, but it will be better for what comes next. So this is like the edge, like the index I, and then the other one would be the index J.
By the way, I mean, just to clarify, maybe I should do this like,
Be more careful. Like, okay, so what is this? I, J, K, L, right, in the alphabet. So let's call them this K and L. There's nothing special about the names that you give to the legs, right? So that's why they're called sometimes dummy indices, right? Like, like they could be called like K, L, like, so there's nothing like kind of like baked in that tells you which one is I and which one is J. That's kind of like arbitrary. But if I'm going to join these two together, right? Like the condition for joining them together is that kind of like they kind of like take on the same values in the sense that if I goes from 1 to 2 to 3, like if I can be 1 to 3, then K has to be 1 to 3, right? So for example, if this other leg or edge had been going taking values 1 and 2, then I should not have combined these together. So like you can combine whichever edges you want as long as each of the indices take the same number of values, which is like the equivalent that when you multiply two matrices, right? Like the inner numbers, like the internal sizes have to match. So it's kind of like the analog to that. So it just like it's almost like imagine that you kind of like almost like a worm. I don't know. You imagine elongating it and it's about to join this one. And right before joining it, yeah, then you change the name, right? Like, so you do change the name the moment you're going to do the contraction, which is how I called this before. But like the names are totally allowed to be different before contracting them. But in order to merge them, then you merge them with their same names because you're going to kind of like add over that index. Okay? So So what this corresponds to in terms of some notation, right? Is that you multiply the entries of the matrix C times the entries of the identity matrix, but we already know that the entries of the identity matrix is this Kronecker delta, right? So you multiply times delta I and J. And the sum takes place over all possible values of I and all possible values of J. So if you're working with n by n matrices, this would be like I and J, they both go from 1 to n, for example, which would be but this is like the fun part here, right? Because the thing about the Kronecker delta is that most of its entries, or like most of the time, is 0, right? The only time where it will give you a non-zero contribution is when it happens to be 1. Everything else, it doesn't count. So it is precisely 1 when I equals J. Everything else is still. So this sum, which started over I and J, you only need to keep one of them because it only, you only have a contribution when I equals J. So this only contributes when I equals J. So that's how you end up with the sum over I. Let me put it like this. I equals 1 to n of CII times delta II, right? But delta II is just 1, right? So like you don't even write this. And so you get that this diagram, oh, I should have emphasized this before, right? Like remember, because now there are no more free edges, this is supposed to spit out a number, right? Like a scalar. So this should have even a scalar. So the scalar that you're getting here, right? What is the scalar that you're getting here? You're getting the sum over all values of I of CII. Like, okay, so what is that? Like, if you were to write this like with, it's C11 plus C22 plus C33 dot up to CNN, right? So you are adding certain entries of the matrix C, actually the ones along the diagonal, right? Like those are like, that is what C11, C22, C33, etc. is, right? So what, like, I mean, maybe you found it from completely, but yes, when then it was a trace. It's just like the trace of the matrix, right? So contracting, oh, this is nice, right? So contracting a matrix with the identity tensor, if you wanted to call it like a tensor, you can just call it like a matrix. It speaks out the trace which in practice people like, don't put like the identity per se. So this diagram is represented as, it's just represented as this diagram. So it means the same, but it's kind of like a shorthand notation for like what I just did, right? So like, so you don't write explicitly the identity in this case, like, just to make it a bit easier. But the idea is that this one spits out, because if you notice, like when you make eventually I and J equal to the kind of the same index for you to get like a non-zero contribution. So the trace of the matrix. And the trace of a matrix, I don't know, depending on how much you have had time to see this stuff before, it is an important parameter in the matrix, for example, the sum of the eigenvalues, but one way to characterize the trace. So, I mean, it is not only the sum along the diagonal, it's also like, for example, the trace of C. I mean, obviously for this, you do need like a square matrix. But otherwise you wouldn't be able to contract with an identity. So it's kind of like the idea that whenever you have kind of like a matrix or like a, like a matrix, and you kind of like join two of these edges, you're kind of like tracing out. That's how you would say it. Like you're tracing out over that index. Does that make sense so far, so good? Well, oh, so for example, okay, it all depends on how you want to set up things, right? Like because okay, so right? Like just to go back to where we started, right? Okay. You want to like say, for example, you want to leave like this one free. If you want to leave this one free, you have to insert something that will fill up this edge, right? So let's say insert a vector, right? So if you insert a vector, right? Then these does, if you kind of go through like the formula, it does spit out like the ith entry of the vector v. So this will give you the ith entry. I mean, like the thing is like again, like these like if you write it all down, like it's a sum over j of Cij times Vj, and that is like the linear algebra formula for like the matrix multiplication of a matrix times a vector. So that it does like these like if as a diagram, if you wanted to just to make it more clear, what I'm saying is that you kind of like, yeah, it's kind of like thinking about it as almost like merging them, so it's like imagine like this one slowly moves to the other one, becomes a big blob, and then the blob is called C times V. Right. So this is like the vector C times V. And this leg represents like the index I. You see, is that making sense? Yeah.
So is there like a notation for like a method like the go back there? I mean, I'll talk about that. I mean, there's kind of like a notation. I don't know to what extent it's universal because, like, this is more recent. But yeah, like, once I talk about grass and cats, I'll say something about that. But for now, like, I'm just being very relaxed. So I'm just putting them, wherever. But yeah, like usually, I think. In the homework, like A B is like B here, but like if we just put them over, that's gonna be A. Oh no, but that's fine. But I mean that has nothing to do with like that convention. That just has to do with the shared index between them, like like how the like yeah, like sorry, like were you going to ask me something? Oh, so wait, vector happening. Right, because if you think of this as kind of like think about this as a matrix, uh, think about this as a matrix. This is a matrix, and then like this is like the formula for the entries of the of C times V. Like the thing is like it's always easy. Okay, psychologically, you can always do a small example to make sure that we're all on the same page. So, for example, if you thought about C as being C11, C12, C21, and C22, right? And then you think of V as being V1, V2, right? Imagine that I have chosen like I to be the index, right? If you choose I to be the index, then you have to put you're having like the sum over j of C1j, right? Times Vj, right? And then j goes from 1 to 2, right? Because those are like the only two values for the index j. And what does that give you? It gives you C11, right? Plus C12 V2, right? Well, wait. So all that I'm saying is that if you look at this quantity, right? That is literally how you would do the dot product between the first row and the vector G, right? Then the J disappears. That's right, because you're summing over it. That's the thing, right? Yeah. That's the point of like the notation. And how do I know that it goes in the first entry? Because I literally took I to be 1, right? Like so if you get taking I to be 2, that gives you like the second entry. Anything more time now? But to answer your question about like the placing of the diagrams, yeah, like the thing is like if you had had two matrices A and B, which I think that's how I wrote the problem, right? If you had two matrices A and B, if you have like the I here and the J here, right? Like
I'm summing over the common index, so I could call the common index K. And it's just that when you work out the formula in terms of like the entry-wise formula, yeah, it does correspond to the sum over K of I k times B K J, and that is literally what ends up being like the entry A comma J of this is like the entry IJ. This is like the entry IJ of A times B. But but yeah, if you kind of like had swap B and A, right? Yeah, if you swap B and A, then it does give you like the K, the sum over B, I K times A K J, and then yeah, like this is like the entry of B times A, entry I comma J. But like the idea is like like the order is more determined by like the important thing is like in matrix multiplication, the kind of like the one in the middle is like the one that's like summed over, right? Oh,
So the edge on the left will always be the first one,
well, I mean,
first index.
well, no, like you could like the thing like the formula is
Like if you had I here, K here.
Right,
why would
right.
you not say A K I instead of AI?
Okay, so you're asking me what if I had just called this J and this one I? That's basically
I'm asking if I is this way. Like you could
Oh.
always call it A K I first.
right. I agree. Yeah. I mean, like
Like what happens if I'm like having three different.
well, the thing is like if but the thing is like if you had three different things, right? Okay, let's see.
What's like the order of choosing which index is it first?
Well, like I think it's just like what I'm trying to say is like yes, it just looks like any like I'm calling them I and J and I'm following alphabetical order, right? So like that's why you're thinking about the order in which they appear, right? But if you think about them as collections of numbers, then the arrangement is like more clear. So let me see if I can be more precise. So for example, right? Imagine like I had written it this way, right? So what does this correspond to? This would have corresponded to the sum over K of what B J K, right? Times A K I, right? And again, like the only thing that matters in terms of interpreting this as matrix multiplication is like this one is kind of like being summed over. So now, but then now this is like the entry J comma I, right? This is like the entry J comma I of B times A, right? So this is like it's just like sorry, J comma I. But there's no like what I'm trying to say is that like yes, it's just like here, once you start giving particular values to the i's and the j's, it will produce like the same answer. Like if you have like well, I mean, like the thing is like I just changed my mind of what I'm calling j and I, right? So to translate, you just if I had chosen I to be 2, you have to choose j to be 2 in this case, right? But like as a convention, yeah, if you wanted, you could always put the I, like in the matrix representation, you could always put the I one to be the left one. But the thing is like with the tensors, right? Once you have like a tensor with 3 indices, like I think this is like what is causing confusion. Like imagine I had like a tensor. I have a tensor with 3 indices, right? And I contracted with another tensor with 3 indices. I don't know, like let's call it S. Is that okay? Right? So what I'm saying is that, right, it is like a reasonable question, like, which one will you call I, and which one will you call J, and which one K or L? I'm saying that, no, that is actually completely random, but once you made a choice, it is unambiguous what is supposed to spit out. That's, I guess, what I'm trying to say. So for example, yeah, like, I don't know, let me follow something not non-conventional. So, there's nothing like in the world that says that I could not have called them like this, right? And it's just saying, and then what this is saying is that, but what these sums do is kind of like a sum of like the entry. Okay. Like, let's call this S, I don't know. Like, and suppose like you could go like, T, well, here, like, I guess you may want to have like this will get fixed maybe once we talk more about grass and cats, because that does make it less ambiguous. But for now, like, yeah, you could move like, the idea is that you would, like, you could move, uh, yeah, you do, like, I guess if I call this TKS, right, like if I'm going clockwise, like like what you're asking me is whether I should read the other one clockwise.
like,
Yeah.
Clockwise, anti-clockwise, and like, is it arbitrary to start from like, say, 180 degrees instead of?
Like, let's see. Yeah, that's like, okay. No, I see now what you're saying. Like, I have to think more about whether that like if you were, yes, let's see. Let me think for a second. Speaking. I think there's like, I mean, I'll check. I do think there's like a convention where you read them clockwise, but also it's because, right, I haven't been super precise about whether like the edges go left or right or up or down, but there is like a precise way to do that, right? Which I think once you, if you do it that way, that does like fix the ambiguity, right? It's just that I still haven't wanted to talk about rats versus cats, and once I do that, then like that, I think does resolve like the issue. But let me get back to that, because yes, like this is like a relevant point, but right now I'm kind of like doing it in a way that's kind of like, a bit sloppy, so that like, we just get kind of like to the computations. But yeah, like eventually there would be like a convention where like, yeah, you don't want them kind of like in an angle, let's say, and so maybe like you want to write, like maybe more write it like this way, and the other two are kind of like maybe going out this way, and the other one maybe looks like this. Well, like again, you could like, um could put it, well, if you put it like this, you could contract both. But yeah, like you have to, this does like, I mean, this does like, helps rid of some of the ambiguity, but kind of like the rule is that, as you do have to make a choice, like for example, these, let's think about like, perfecting like the notation. If you just wanted to draw them horizontally, or, if you wanted to draw them all horizontal, right? Then I think there is this convention when you kind of like read them clockwise, but like, if as long as the indices run in the same, as long as they kind of like both the indices run with the same number of values, then yeah, you can merge these two, or you can like make an overlap, and those are variations. But yeah, like you do have like, I agree, you do need like a convention on how you want to read them. So I do agree with that, but like I don't know, like if like getting into what the right convention should be before we discuss brass or cats could be like a bit messy. So it's better to talk about that first, and then I'll set up like a convention, for how we unambiguously would read it. Would you want to?
Of the, like, this would combine with the indexes or grass, so.
Well, no, but it is true, like, like in the sense, like, if like something happened, like I guess like although I'm saying, right, like, yeah, like it is true, like, like, yes, like the tensor is like Tijk, right? It's more like, whether we want to have like a preferred way of drawing, like calling one edge I, another edge J, and if I were to draw it like this, uh, whether I want them to kind of like move clockwise or counterclockwise as you read out the diagram. That's all the only thing we're debating. I was just saying that yes, there is a convention, but it's not a universal one. So I still haven't made up my mind of what's the best way to present like the conventionality part, No, like that's, I mean, once you have, how should I say it? Once you have, you can always translate between one convention and the other because it's kind of like similar to this diagram, right? Here I changed my convention of which edge I called I and which one called J, right? And so whenever you find an answer here, you just have to remember that if I call this I comma J, this is being called J comma I. So like I mean, there's always like a way to kind of like parse out what what it means. So it doesn't all that I'm trying to say is that at this moment it feels like it causes more ambiguity that it ends up causing because it's not as bad as like it seems, but like, we do have to have like a distinction between brass and cats that does help clarify some of these things, like or vectors like covectors, which is like the other name for this thing. But I'll get to that in a moment.
Might be totally unrelated to this kind of cancers, but what I read about it is that in like, if you're writing it in, for example, Einstein notation or something, then it does not matter in which order we write the indexes, but if we are multiplying two tensors, say like B, JK and A, KI, then the indices we want to multiply should be corresponding to each other. So for example, BJK and AIK should be the things. So
Oh no, right, like
these
yes,
should be in the same place.
yeah, no, like that is completely correct, and this is kind of like related to what I was saying earlier, like that like at this stage you're kind of like free to call whatever like like the dummy indices you want, but then before merging them, you do have to agree that they will be relabeled the same. Yeah, no, that's fine. It's more like a as a preference, whether we have like a preference when we read out the names of the diagrams clockwise versus counterclockwise, but it doesn't cause like issues like when it comes to computing. Like you just make a decision and then you go with it.
No, I was like saying when you multiply them together.
Oh no, yeah, no.
That
For
time
the
you
right.
write the indexes kind of corresponding to each other,
Correct.
so they die out.
No, exactly. No, like for the when it comes to the contraction part, yes, like you cannot right, like you have to sum over like and then you'll have like the same
order.
Right, exactly. Yeah, no, that is correct. Now the thing I was okay. What's definitely true. Maybe just to kind of this is the last example of the diagram before saying something slightly different, but it's still interesting. Like for example, in this problem I had given you, like, which we already talked about another example. Right. I mean, I'll just give names to like the thing is, it's also like in tensor networks, people usually don't even label the edges. Like in that if you look at the picture, that's why I'm also thinking, okay, what's like that standard convention for labeling the edges because we don't even see them labeled. So that's where I'm not. Okay, but in this, like, let me not label the one that's being summed over just to make our notation a bit easier. So okay, we are in agreement that maybe that should be kind of like the entry ij of A times B, right? And again, if you kind of merge these two together, right, like the only ones that are left, like let me, okay, I will even delete that because I'm summing over it. So this actually, because of what we were talking about earlier, like connecting them actually gives you the trace. So this would be the trace of A times B, actually. And the thing is like, one of the nice things that makes this perspective nice is that it gives you kind of like suggestions of certain formulas. So for example, if you imagine like these are kind of like wires and these are balls that you can move along. So you could kind of like move it here and then, kind of make it come the other way. So like, it's almost like a train, right? Like a railroad. So like imagine like, let me see, like, just imagine grabbing this ball. And now it's like gets to the other side of A, right? So if you do it, can everyone see kind of like the animation, right? Like is that because like you keep track of it. And that yes.
All the, company traits of like all of them.
Oh no, that's the thing. Like remember, this was kind of like the notation that's why I introduced this notation earlier, because what I was saying is that what I mean when I close it off, right? What I mean when I close it off, it was kind of like inserting this identity, but when you insert the identity, you do it over all, but only the ones that survive is when I equals j. That's why you only get like the elements along the diagonal. That's why like but like that's a like but the convention is like no matter the name of this thing, whenever you put for the matrix, whenever you connect its two edges, like it will spit out the trace of it. So in this case, like uh let me go back here. Once you like don't get like confused by the name, right? It's just that you're giving the fancy name A times B, but you could call it C. If you call it C, when you merge the edges, that's just the trace of it. You see, so like it just all that I'm saying is right, like these two kind of like are brought together. But just called C A times B. Do not get confused by the name, right? And then the instruction for connecting them, the way we define connecting the two edges was kind of like inserting the identity matrix, but that what ends up being equivalent to taking strength. You see, so that's why we end up with the trace of C, but C happens to be A times B, right?
So you're saying like, oh, if you had the matrix of I and J,
Right.
those are the identity matrix.
Exactly.
You do the formulas would look like C. It's like,
Right.
and that's, okay.
Well, I mean, you can, okay, let's see. You have to connect in pair, right? Because it's kind of like also like with, like, like if you have like a third order tensor, right? You can only connect two at a time because like you cannot add twice over the same index, if you know what I mean. Like, once you do a contraction, like that index disappears, right? So it's not really out there anymore. It's like, so actually it's like, because this only has an index left, it's actually like a vector. And then like, yeah, you can contract a vector with another thing, but if you had four indices, then you can do 2 and 2, right? Like, so yeah, like. Correct. Well, no, like if you like, if you two of each own tensor, right? Like if you, this is like very fun, but if you like, there are no more open edges, so there is a number. Yeah, it's it's just like, but it's kind of like it's kind of like not like a trace I mean, it's kind of like a sort of trace. I guess this would be kind of what like a sum of or like TI, JJ or something like that. You have to work it out, you know. But it's still like a number, you know what I mean? Yeah. It can get complicated, like you should do that for sure.
But I mean, but one way to think about it would be, the one way to make sure to find out the correct formula is to put that identity on it to make sure like it kind of like works that way. That, you know, actually that could be like that's not my problem with it. In fact, whether what you should get like this. I'll add it because that's a cute one. All that I wanted to say is that if you kind of like take the diagram somewhat seriously, where it feels like you can kind of like move the ball around, this kind of like should suggest that like this. I mean, this should be the trace of BA. So this would suggest that the trace of A times Z is the same as the trace of B times A, which is actually correct, right? That is like a property of the trace. In the same way that the determinant of A times ZB is the same as the determinant of B times A. So it's kind of like a chicken or egg type thing, you know, of because you already, I mean, you can prove that these two things are the same. And so you can reinterpret that as being, oh, it actually is fine to move it around. But I mean, in a parallel universe, you could have started with the diagrams. And this is actually that people do in things called like category theory and other like things like that. You start with the diagrams, like the rules for the diagrams, and then it kind of like from the rules of the diagrams, like you get that the traces like, you know, of A times B, like the same as the trace of A, B times A. So all that I'm saying is like the tensor notation is more flexible, you know, that you would see at first sight, and it kind of like, you know, getting acquainted with that flexibility is one of like the things that make you go faster, you know, when you do calculations, because it actually you can, they're not rigid, like, you know, you can kind of like move things around like that. So that's what. Is that what you said?
So you're saying like the trace of like AB, BA, those are the same.
Yeah. No, and that's like an actual result in linear algebra, right? So you can, again, never in linear algebra, I bet, where you show these diagrams, right? Like, so you just say like the trace of a matrix is the sum of the diagonal elements, right? Prove that you know, that for A times B, it doesn't matter which, you know, whether you do A times B or B times A. Same with determinant, right? Like, you know, determinant of A times B is the same as determinant of A. So it has like a non-complete, like a non-visual proof, like a completely 100% legit non-visual proof. All that I'm saying is that if you can like think that this is more than a nice thing, like, and you kind of take it seriously, it suggests things, right? Because if you had not, this would have suggested like something to prove, right? Like, you know, you could have, if you had not tried to prove this, it's kind of like suggest, oh, maybe you should try to check out whether this is true or not, right? And then if you are kind of like more like algebraically oriented, you would still be like, well, let me check it from the formula itself, which is totally fine. But it's nice for the diagram to kind of like suggest things. So all that I'm saying is that these things do come up with suggested or for the formula to like. Yeah. Okay, so like in the remaining minutes, so far, like the tensors have fall from the sky. I haven't really said where the tensors come from. Like I just said, well, let's say you have a tensor here, you have another tensor here. But you know, a useful question is how do you build tensors? So this is like another important question to discuss. Is there a way, like a natural way to produce tensors? So let me go over that. And there's a natural way, which is called like the tensor product. So the tensor product is the tool to build tensors, okay? So like it's some sort of multiplication, you'll see why in a moment. Because it's some sort of multiplication, you can like, you know, use a usual symbol for multiplication, like an X, so you put like a circle around to distinguish it from the cross product. You don't want to make it messy. Okay, so let me start with the most basic example, which is two vectors of size 2. So this is like the you know. So here's, and from there you can build to more complicated situations. Okay. So you have two vectors with two entries. I will cheat a little bit, think of them as, you know, matrices. So this would be a 2 by 1 matrix, right? And this would be a 2 by 1 matrix, right?
So if you know, you could imagine someone giving you this as a problem with matrices, right? If someone said, okay, you have these two by one matrices, how could you multiply them just using regular old-fashioned matrix multiplication? So you cannot, you know, you cannot do as matrices. This is not allowed, right? This is not good because the sizes don't match, right? Like this would be 2 by 1, and this is 2 by 1, and we don't know, and we know that this is wrong, right? Because like they don't agree. And you know, like another possibility is just to flip one of them, right? So this is bad. Okay, but for example, you could transpose the first one. Again, think of this as matrices. So like I'll transpose it. So I'll do U transpose times V. So now this is 1 by 2, right? And this is 2 by 1, right? And I mean, if you work it out direct, you know, this is U1, U2, right? Because the transpose becomes a row vector, right? And then this is V1, V2. And what does this correspond to? This is just like the dot product, actually. This is just like the dot product of the two vectors, right? So this is U1, V1 plus U2, V2, right? But like there was an alternative, which being around the result, and you usually don't spend too much time talking about it. But there's like another alternative, which is like, well, what if you transpose this one instead? Like so, you can decide where to transpose. So right, like imagine if you had done U times V transpose. Okay, so this is 2 by 1, right? V transpose gives you 1 by 2, right? So this is fine, right? Because there's agreement in the inner one, and so you would end up with a 2 by 2 matrix. So this operation is supposed to produce a 2 by 2 matrix, right? So this will be 2 by 2. And this I will call that, well, let me write first the entries, and then I'll call this, give it its name. So if you work it out, let me put this a bit lower. So this is, it's a bit confusing to do the multiplication because like the vectors are so small that you kind of like, hey, you know, you can get confused by it. But because like the vectors only have, you know, the row only has one entry. So you do first row with first column, but each has one entry. So it's just U1, V1. And then first row with second column, but again, it only has one entry. So it's like literally like just regular multiplication. So you get U1, V2. And then second row, first column, U2, V1. And second row, second column, so that gives you U2, V2. Is that okay? Is that kind of like plausible, making sense? And so this matrix, because it's built out of U and V, is what you would call U tensor V. So this is like the tensor product of U with V. Yeah.
Let's see, basically, since it's just a vector, it's just a big vector. And what direction matching principles say, and basically you multiplication to big vector. So basically, like, you added actually well, let's, I mean, like the only, I don't know, like if I would call this like adding extra dimensions only I mean, if you told me like adding extra dimensions for me literally means like adding more entries, right? Like here I'm just like reinterpret them as matrices, which I agree, you know, that is not like a natural thing to do with vectors, right? But if you thought about them as matrices, so like what I'm doing is like taking two matrices of the same size, right? Because I started with two matrices of the same size that just happen to coincide with vectors, right? And then multiply them in the old-fashioned matrix way, right? But it's kind of like, but I wouldn't call it like increasing their dimensions, because for me, increasing their dimensions would kind of like mean more like that you added more entries to the vector itself, you know? Oh, no, no, yeah, yes, no, yeah, I'm about to write like the formula That's where I'm headed, yeah. But like, I just wanted it to kind of like, you always start with the baby example and then like build up, well, I will get to that like next time probably. Yeah, but that, yes, like, it will come, yeah, it is related to partition product if you work with finite sets, yeah. Okay. Will you go back to that? No. Partition product, something crosswise. No, so partition product, it just means like ordered pairs, but I mean, I won't pay too much attention to this right now because like if you had like a set like 1, 2 and another set which is 3, 4, then the Cartesian product is not like all the possible order pairs. So 2 times 2 is 4, so like there are 4, it's like 1 with 3, 1 with 4, 2 with 3, and then 2 with 4. You see, which is kind of like more like a discrete operation because you can do it with sets without any structure whatsoever, just like a list of finite numbers. But I don't want to, like there is a tensor operation with functions. We're talking about talk about that later, like next week. But for now, I'm kind of like trying to do something a bit more concrete. So that we can do that. So is it cross product? I mean, that's just like an accident because like literally, like
So it's not.
right, because like the idea is like they give it like the same notation because like the context should be unambiguous enough that you never confuse them. So like that's why no one like otherwise you can have to like writing these tables for everything. But yeah, like yeah, so it's just like an accident that is the same same. I mean, if you think about it, like even the cross product is the same. I mean, in a sense, it's almost like the same notation as you know on a calculator, people write 3 times 4 as being 3x4, but no, you don't say, oh, is that a cross product? You know what I mean? Like, so like, like, yeah, at some point, like you just run out of symbols and even the number pi, like the number of ways in which the symbol pi is used, is insane. Like, it's like for the circle, but sometimes that's used for probability distribution and sometimes it's used for other things. So sometimes when you have to, or even pi, right? Like, so yeah, but it has definitely nothing to do with the cross product stuff. Right. What I was going to say is that this is where like it's convenient to think about it in terms of entries because what this is saying is that the entry, like the entry I comma j is just ui times vj if you think if you kind of like go through like the formula. Like, and so if you had 3, I think you were asking me about the 3 one. Like if you had U cross V cross W, right? Like, let's assume that they are all of size 2 just to make my life easier. If you had like U cross V cross W, then I would give it I, J, K entries, and this would be U entry I of U times entry J of V times entry K of W. You see? And from there, like, you can keep generalizing, but it's just like, how many dots do you want to write? Because it's just like, once you understand the idea, obviously you can continue with 4 or 5. So basically you just, right, what this is saying is that when you take the when you take the tensor product of 2 vectors, you do get, you get a matrix or like a 2 tensor, right? So like I can draw it like, I don't know. Again, like I'll just draw it diagrammatically like this. And when you take the cross product of 3 vectors, like you would get something like this. Okay. But I actually want to like I do want, obviously this is like a super important operation, like the tensor product operation is like really, really crucial for a lot of this stuff. But let me just stick with the matrices for a moment. And so for example, if you had like 2 vectors of size n by n, right? Sorry, like of like with n entries, if you had like u being like u1, u2 up to un, right? And v being, because I do want to finish with something like fun to in the last 10 minutes. So if you had u n entries and v with n entries, u cross v would have an n squared matrix, right? N by n matrix. So u cross v is an n by n matrix.
is a square. Which again is kind of like would be U1, V1, I guess U1, V2 up to U1, Vn, and then U2, V1, U2, V2 up to U2, Vn, and then you go down to the end, and then it's just like UN, V1, UN, V2. Okay, and then UN, yeah. So this again is like the U cross V matrix, like or like the tensor product representation. So this would be U cross V. Okay, so here's like a fun question that we can kind of like more or less answer in the remaining time. Okay, this happens to be a particular matrix, right? This is like a square matrix. So here's like a cool question. So question. If you had question. If A is an arbitrary n by n matrix, right? Can you find two vectors U and V such that A is like the tensor product of those two, right? Can you find vectors U and V such that A happens to coincide with their tensor product? I mean, obviously, sometimes you can do it because you can cheat. You can start with two vectors, right? You take the cross tensor product, and that gives you a matrix. But I'm kind of like going the other side, right? Like I'm saying, if you start with a random matrix, can you do that? Yeah.
No, that has to be random. They, like the cross, the tensor product of two vectors that has to be ranked one.
Yes, like, but that's not kind of like a too much of a fancy answer for now, but that is correct. That is like the correct answer. But there's like an easier answer that you would not like, that is true, but like you can do also like a parameter count to just convince yourself that I mean you can okay, first yes, let's just start with n by n. So if you have like like a random n by n matrix is specified by n squared numbers, right? N squared entries. So if n, A requires like if it's completely random, it requires n squared numbers, right? If you were able to find U and V, each U and V requires just n numbers to specify. So U and V both would require two n numbers to specify, if that's making sense. And this is kind of like complex, counts of like efficiency of like algorithms perspective where you see, just like in terms of parameters, whether like the parameters match. So U and V each would require n entries, right? So if you were able to find this, like, if this always worked, you're kind of almost saying that the space of matrices, which has n squared parameters, can be decompressed in a sense, like, into a space that only has two n parameters, right? So 2n in total. And like that kind of like seems odd, right? Like you wouldn't expect that to happen because, one thing like a priori, larger than the other. Like n squared is larger than 2n in general, right? So this is kind of like a rule of thumb. Then you can give like a more precise answer, which is like the one that you're given that it only happens when the rank is 1. Yes. Yeah, but I'm just saying like this is kind of like a useful rule, like what like people physicists sometimes call like back of the envelope calculation, where you just kind of like count what's like how much freedom around you have, and then you see you have n squared degrees of freedom here, but with two vectors you have n and n degrees of freedom. So like it would be weird like if every matrix could be written in terms of like two vectors. So So in general, you wouldn't expect this to happen. Wouldn't expect this to happen. But
But my argument does fail. There's only one case where 2n equals s squared, right? That is when n equals 2. So the thing that I just said, like it is plausible. It does seem very plausible when n is larger than 2, but like maybe there's still this tiny shiver of possibilities that, with 10n equals 2, that would be like a possible. But what if n equals 2? And I'm almost done. So what if n equals 2? Okay. Because they're like 2n equals n squared, right? Here. So obviously, like what I'm trying to say is that here, like the parameter count argument does not work, right? Because you have the same number of parameters. So you have like need to do something more clever. And so if you have like, if you thought of, and I mean, this is like like a way to think about it. If you thought about the matrix as being A, B, C, D, right? We already had, this was U1, V1, U1, V2, right? U2, V1, and U2, V2, right? Here, like, it's something that shows you why this wouldn't work in general. What is the determinant of this matrix? The determinant of this matrix is, I mean, I don't know what the matrix is, so it's just AD minus BC. But what is the determinant of this matrix? The determinant of this matrix would be U1, V1, U2, V2, right? You have to multiply this element minus U2, V1, U2, V1, U1, V2. Can anyone notice what happens with the determinant here? It's zero, like it's just like always automatically zero. And at least we do know that there are 2x2 matrices with non-zero determinant, right? So in fact, like yes, like this is related to the rank of the matrix, which I think is like a better moment to kind of like talk about it like next time. But all that I'm saying is that so in general, a matrix cannot just be written in this way, but a random matrix, but here's like the good news. If A is arbitrary, like it can be any size, A n squared matrix, you can write it as a sum of tensor products. So you can express A as a linear combination of like, I don't know, like, oh my God, UI tensor BI, where I equals like goes from 1 to some number R, and R, like the minimum R that works in the sum is like the rank of A. So R is like the minimum, the rank of a matrix, the rank that you have heard from linear algebra, when you row reduce the matrix with Gauss-Jordan, you have like the number non-zero rows. That same rank is the same number of the minimum number of summands that you would need to express a matrix as a linear combination of tensor products. So that's like a very useful idea. So the minimum R that works is called the rank. It is the rank. And we'll talk about this like in more detail next week because this is like a super important idea. But the kind of, in a sense, the lower the rank, the more simple the matrix is. And so the rank is or the tensor. Like it will be a definition of rank for tensor.
So that means that you can take like a smaller simple and then like a vector information. So you can make higher and higher tensors. But then if you want to go back down, higher tensor, the lower tensor you can still be like that.
Well, I mean, so the thing, so the way I'm presenting it, like, I mean, if you start just with a scalar, you are really stuck on a scalar because a scalar is 0 by 0, right? So they're like, you cannot kind of like build like with Legos with a scalar. But yeah, you could take with like, you can take with vectors, right? You can start tensorizing the vectors if you want to call it that. And that does build like more and more complicated tensors, right? And if you wanted to, right, not always can you if you have like a random tensor, it's not necessarily just like a product of those, but they're they are like kind of like the building blocks, kind of like a basis almost, where they form like a basis for all the tensors. So any tensor of a particular dimension will be a linear combination of the tensors that you get just by tensorizing like a basis. I mean, I would say that more precisely next time. But all that I want you to kind of have like a sense is like kind of like the rank is a measurement of how complex the matrix is, or the tensor. And I'll give like the definition for tensor, like rank of a tensor next time. Because for example,
if, what does that mean? If a tensor, like, or a matrix has rank, you know, one, like, then means like you can store it with, like, 2n numbers instead of n squared numbers. And that it makes a lot of difference if n is like 100,000, what do you prefer, 100,000 square versus 200,000? Like, you know what I mean? Like, so once you talk, and this is where you can see some of the machine learning or like all this stuff, like statistical mechanics also make creeping in. Because once the numbers are large, n squared versus 2n is like a massive difference. Or even like something with like where you have like a bound on the rack. It doesn't have to be one, but controlled by some quantity. So that's how all these a lot of approximation algorithms work, where you try to find like a low rank approximation to a tensor, like, or low rank approximation to a matrix. And we'll talk about all of that starting next week, because this is like a super important topic. So like this is like one of the takeaways I want from the class is kind of like how important the notion of rank is. But let's finish here because I'm done almost with time. So maybe add 1 or 2 problems for you to work over the weekend. But do next week, but not at the beginning, so that if you want to ask me like one-on-one, you can, like, if you're stuck or anything. But I'll just do that. And I'll send you the notes later in the class, after class, once I get finished.